Hi everyone, welcome back. In this video we're going to be talking about some useful and important constructions dealing with functions before we get back to our main material. And so the first thing I want to talk about is this idea of composition of functions. So imagine we have two functions which are linked in some sort of way that we're going to see. So we have our first function f, which maps from a to b, and we have our second function g, which maps from b to c. And so the way that they're linked is that the domain of f is the same, or sorry, the range of f is the same as the domain of g, right? So they're both the set B. And so f maps the elements of A into B in some certain way, so we can picture this as something like this. And by the way, I don't think I made it clear in the last video, but the way in which I draw these lines does not matter. All that matters is the endpoints. So which point gets associated to which point. You know, if I curve it in some sort of way, that doesn't actually matter. I'm just being creative. Okay, so let's say this is A. This gets mapped to f of A. And now we have a function g that maps elements of B into C. So I probably should have used different colors, but I'll just use a different color for this one now. So this will go here. This will go here. Okay. So these red lines I'm saying are the mapping through G. So this point here will be G of f of A. Right? F of A is the value of f at A, which is some element of B, right? Because f maps into B. So f of A is one element of B, which we can then map through G. So that value then would be G of f of A. Okay, so our notation makes sense. And so we can see then that through this process of mapping through f and then G, we've kind of constructed a mapping from elements of A to elements of C. So if we look at, come on, where this element maps to, okay, it maps to this, wait, what? Yeah, okay, never mind. Yeah, it maps to this element of B, which then maps to this element of C, right? So I can directly go from here to here, and A maps to G of f of A, right? So, I'm warning, this picture is about to get very messy, but hopefully the colors help. Okay, and our last element of A maps here. So the point is, in the end, we generate a new function from A to C, right? So we have this function that goes from A to C, and it's such that this new function, which we're going to give a name in just a moment, that evaluated at A is equal to G of f of A, right? For any element of A, this is how it maps elements of A into C. And so what we call this function is G, sorry, I keep hitting the erase button by accident, G composed with F. and we use this open circle to denote the composition. So I'm pretty sure you've seen this notation before. You probably just don't remember it. That seems in my experience with teaching high school students composition of functions. So we have g composed with f. That itself is a function, and we evaluate it in the domain of f. And the range of this function is the range of g. Okay. To give a physical example, this is kind of my favorite one to give, is that we're well aware of the concept of potential energy, right? It's this energy that depends on the position of a particle, and in the actual physical context, it gives rise to the forces by if you take the minus gradient of the potential energy of a system, then it gives you the conservative force associated with that potential energy. Okay, that's not necessary for this example to know, but just talking about in general. So usually we'll be dealing with three-dimensional space, right? And each point in this three-dimensional space, so let's say this is our vector, position vector x, we can associate a potential energy with that point, which is our function u of x, right? So our potential energy is a function u which maps from R3, right? This is basically saying it's our 3D space, right? So we represent it by an order triple of real numbers, right? 3 real numbers. And it maps to just R, a real number. And so the idea is that we're mapping from a vector to a scalar. Okay? But what we also know is that if we're considering an actual particle following a trajectory, that trajectory, or the position of a particle, is given as a function of time. So this x is actually a function from R to R3. Now, what is this R? This is time. And this is space. And then just to note here, this is space, and this is energy. Sorry, I keep hitting that erase button. It's just on the side of my pen, so I just keep accidentally pushing it. Okay. So, what we might have then is an actual particle goes along some trajectory throughout the space over time. And what we want to know is, as a function of time, what is the potential energy of the particle? This is actually a useful question, in particular because if you then get the potential energy as a function of time, well, now we can differentiate this with respect to time. And that could be relevant because if we add that to the derivative of the kinetic energy, let's call it k, we know that this is equal to 0 because the total energy is conserved through time. So that's one reason why we might be interested in the potential energy as a function of time. Okay, well, how do we get the potential energy as a function of time? Well, let's say we know the trajectory of the particle. We know how its position changes over time. So we know, let's call it x of t, which is really this function. and we know the potential energy function. So the potential energy at each point in space. Well, this particle is going along this trajectory, so we know how to go from the time to the position at that given time. And then because we know the potential energy function, we also know how to go from that position to the potential energy at that position. Well, if you look at what this is exactly the potential energy composed with our position as a function of time, just evaluated at time t. So what we're looking for as the function that is the potential energy of the particle over time is exactly u composed with x. And you'll usually see this written as, well, what I just put before, u of x of t. Okay? So this is very relevant to what we do, and not just for this reason, but for many, many other reasons. But this is just something that I like to bring up because I think it's very intuitive for people who are familiar with physics. Okay, so what is the next thing I want to talk about? Well, I want to connect our discussion of functions to your previous knowledge of graphs. So we talked about how functions map elements of a domain into a range, right? They're associating elements of different sets according to this, according to however it does that, but we need to have this rule of well-definedness, right? At the very least. Okay. Well, consider that f will map a specific element a to f of a, right? It does this for every element a of the domain. So what we can construct from this is then a set of ordered pairs a f of a, such that a is in our domain. By the way, I'm doing this for an arbitrary function f. I'm not connecting this back to this stuff. Okay. Well, let's think about this. A is in our domain. F of A is in our range, right, which we call B. Now, what was the set of ordered pairs of elements in A and then elements in B? Well, that was exactly A cross B. So here's where I'm fulfilling my promise about the connection to Cartesian products. We have this representation of the function f as a subset of the Cartesian product of the domain and range. So we can think about the function as these ordered pairs of or argument, right, along with its value, right, its corresponding value. And you're like, okay, whatever, that's something we can do. That's kind of abstract. Sure, like if I have something like this, this kind of setup, I can associate these points, and then I can consider the function as really just being, this ordered pair of this point with this point, and then an ordered pair of this point with this point, and an ordered pair of this point with this point. It's like, okay, why should I care? Or why might this be important to me or interesting? Well, if you think about, let's say your domain and range are the real numbers, and you think about, okay, what are these ordered pairs in that context? Well, in that context, maybe I'm revealing too much right away, but those ordered pairs, if they're just real numbers and you're talking about, a function that's like, you talk about f of x, well, the ordered pair would be x, comma, f of x, right? This is our input, and then along with it is its value, its output. Okay. And just as we said here, we're considering the set of the ordered pairs of this construction. Well, this is an element of R cross R, right? Because in our example here, f is a function from the reals to the reals. So A cross B is R cross R, which is equal to R2. We know R2 is this 2D plane. So that means we can plot these ordered pairs in the plane. And so for each element x in the real numbers, we can plot a point in the plane that corresponds to x f of x. Okay, well, I can do this for all the elements x. It's going kind of slowly, but I think you'll see the point. Okay, so basically I'm imagining that I have this function. I just plotted this ordered pair construction for the elements x in the real numbers that I can imagine. And you can see if I actually did this for every single x, what I get is exactly what you guys would call a graph. Huh? I feel like that, that has to be pretty cool, at least for you guys. And so that's exactly why we call this thing, this set, the graph of f. So we've made this abstract generalization of the idea of a graph, and we've seen how, in the cases that we're familiar with, it actually corresponds to what we are familiar with as the idea of a graph of a function. Okay? So these are both very important ideas. I think the graphs kind of help to solidify the connection between functions that you're used to, functions that we're actually going to be interested in now. And compositions will come to play an important role with what we've done with injectivity and surjectivity, and we'll see that in the next video. All right, see you guys there.